Hi, let us proceed with our discussions on the testing of a beam in the heavy structure lab. Previously, we talked about the testing procedures of a 4-point load test. It was mentioned that we need to conduct the testing carefully in order to acquire good result. You may refer to the relevant standard, follow strictly the guideline in order to test the specimen. If you cannot find the relevant standard, you may refer to other standard having similar natures of the testing, adopt the principles and procedures, apply into your research. Or you may refer to the previous researcher, mimic the testing in order to carry out your research. We also mentioned that the test procedures comprises two main parts. One is pre-test stage, another one it will be the testing stage. You need to ensure everything is in place before you can start with the testing. During this pre-test stage, you are preparing the specimen as well as the test setup. Apply a little load onto the specimen in order to consolidate the specimen and the test setup, which at the same time you check the validity of the measuring instruments. There are some precautions here. You may use additional instruments to be installed to the testing frame in order to check the stability as well as the deformations conditions of the testing frame, and also check the test setup, tighten the connections and others. Once you have everything in place, then you may start doing the testing. You can increase the loads gradually at certain interval. Hold the load for at least 1 minute before readings are taken. The purpose here is to ensure stress is properly distributed throughout the specimen before readings are taken. Throughout the test, you will need to monitor the load displacement response of the specimen. This can be done by plotting the loads as given by the load cell against the mid-span displacement as given by the LVDT. This shows a typical load displacement response as acquired from the testing. Monitor the load displacement response in real time. This will help you to make a lot of important decisions throughout the testing. Knowing that the testing can only be done one time, therefore, you will need to monitor the load displacement response carefully. Throughout the testing, you will monitor the progressions of the plots on the curve to ensure a smooth load displacement curve. Make sure the plots are more or less equally spaced throughout the entire curve. If you find the plots are too closely congested, you can enlarge the load interval. Or if you observe the plots are too distant apart, you can narrow down the increment interval. The load displacement response also help you to identify the stages of the specimen. For example, at the early stage, the specimen remains more or less elastic. The development of the displacement is slower. And then at the later stage of the testing, the displacement of the specimen increased faster. In order to ensure nice plot throughout the testing, you can swap between the load control mode and the displacement control mode for the load increment interval. What does it mean by the load control mode and the displacement control mode? The load control mode means that the increment interval is based on the load interval. For example, 5 kN load. You will progressively increase the loads at an interval of 5 kN during the load control mode. As for the displacement control mode, we will decide the increment of the load level based on the displacement. For example, for every 2 mm displacement, readings are taken. This slide compares the different modes that you use during the testing, which will affect the load displacement curve. The first method here is a combined mode, where you start with the load control mode and followed by the displacement control mode. Normally at the early stage, the displacement develops slowly, and then at the later stage, the displacement increases rate. Now your reading at the early stage is depending on certain load interval, and then as the displacement accelerated, now readings are taken based on the interval as defined by the displacement. This will give you a more refined plots when the displacement increases rapidly. Now if you apply the loads fully based on the load control mode, this will be the outcome. In the early stage, you will have nice plot throughout the curve, but when the displacement accelerated, you have less plot. When you do not have plots in between the actual plots here, the response at this stage it will be imaginary, as predicted and forecast based on the interpolations between the two plots here. By comparing these two methods here, the combined mode here of course is giving you a good curve, especially at the later stage of the testing. Now if we use the displacement control mode throughout the test, it may lead to you situations where the plots at the early stage of the specimen further space. By looking at the same set of data here, in fact this one is still okay. Personally I feel this one is more crowded. This one looks okay to me. However, there are situations that the early stage of the testing may end up to be very less refined plots. In this case, when the plots are limited at the early stage, what is happening in between the plots, it will be imaginary. Now this comes to your wisdom in determining the intervals. If you find the plots are too closely spaced, you can enlarge the intervals here. If you feel the plots are too further away, you can reduce the interval. That's why you need to monitor the load displacement response of the specimen in real time. As once the testing started, you cannot redo the testing. For you to determine the maximum capacity of the specimen, you will seek for the highest loading achievable by the specimen. This is achieved by observing the peaks of the load displacement curve. Theoretically, once we confirm the peak, we can end our test. Now the question here is, how do we know when shall we stop testing? This can be determined in two ways. The principle behind it is to confirm the ultimate state of the specimen. Once you observe the plot has peaked, then you suspect that the specimen may have failed. To confirm that, you can proceed with the loading and observe if the specimen can gain further strength. If the following readings can give you higher strength than the previous one, that means the beam can withstand more strength and the ultimate load has not yet achieved. But if the following plots here cannot go higher than the previous one, for at least 3 consecutive drops, it is likely that the ultimate capacity has been achieved. If you want to know for sure, you can have more plots and to observe whether the strength can go higher than that. Some may choose to go for a more conservative method, seeking for 20% drop from the highest point. By the time the load capacity reduced 20% from the highest strength, it is nearly definite that the specimen has failed.